Welcome to this explainer. Today, we're diving deep into the dense, hours-long broadcast of Mission Aagaman to uncover exactly how Skyroot Aerospace launched India's first private orbital rocket, Vikram 4. This was a monumental day, right? Not just for a single company, but for an entire nation stepping into the global private space race. We're going to break down the engineering, the physics, and the massive economics behind this incredible leap to the stars.
Okay, let's set the stage here with a truly staggering number. When Vikram 1 sat on the launch pad at the Satish Dhawan Space Center, it weighed a massive 45,000 kilograms. But here is the mind-bending part. A full 90% of that weight was just propellant. You see, because rockets don't have the luxury of using oxygen from the air like jet engines do, they have to carry absolutely all their fuel and oxidizer with them. Every single second of flight, the rocket is getting lighter as it burns and throws that mass away just to fight the relentless pull of Earth's gravity.
Section 1. The arrival of Vikram 1, from startup to space tech unicorn.
Now, Skyroot didn't just build this rocket overnight. It was founded by two former ISRO engineers who imagined building a globally competitive space company right out of India. And to do that, they had to pull off a massive engineering leap. Traditional rockets have always heavily relied on metals, which offer great brute strength, sure, but they come with a severe weight penalty. Skyroot entirely abandoned that traditional metal framework. Instead, they built Vikram 1 using advanced carbon composites and 3D printed parts. By weaving together fine strands of carbon fiber and using a specialized resin, they created structures that are 5 times lighter than steel. This gives the rocket an unprecedented strength-to-weight ratio, making reaching orbit far more efficient. And honestly, this exact innovation is what helped them become India's first space tech business valued at over $1 billion. Section 2. Engineering India's private rocket, the anatomy of Vikram 1. So to manage all that mass we talked about earlier, Vikram 1 relies on a highly specialized staging process. We're looking at a 22-meter-tall machine, essentially 1,000 interconnected subsystems with absolutely zero room for error, divided into 4 distinct stages. The first 3 stages, the column 1200, 250, and 100, are solid rocket motors. These provide the raw, brute force needed to punch straight through the dense atmosphere. I mean, just the first stage alone generates 10 times the thrust of a single Boeing 737 MAX engine. That is wild. But once you're up in space, you need finesse, and that's where stage 4 comes in, the Raman Orbit Adjustment Module, or OAM. This liquid-powered stage offers surgical precision to place the satellite in its exact intended orbit.
But how do you actually coordinate all that fire and fury? Well, the rocket relies on its avionics. As the source material beautifully puts it, avionics is the nervous system of the rocket. Without it, the rocket is flying blind. At the very core of this network is the mission computer, aptly named Ramanujan, after the legendary Indian mathematician. This computer makes crucial real-time decisions in literal fractions of a second. It processes data from gyroscopes and sensors to distinguish between the rocket's actual trajectory and intentional structural flexing, ensuring the whole vehicle stays perfectly on course, even during extreme aerodynamic stress.
Section 3. Brute force and precision, conquering the physics of space.
All right, we really need to understand what these rockets are actually aiming for. A lot of people think orbit is just, floating around in zero gravity. Actually, scratch that. It's more like a state of perpetual freefall. Gravity never actually lets go. To achieve orbit, a spacecraft has to move sideways at an immense speed, about 7.6 kilometers per second. It's moving forward so unbelievably fast that as it falls, it continuously misses the Earth's surface. That's exactly why the rocket performs a gravity turn shortly after liftoff, efficiently accelerating around the Earth rather than just going straight up and away from it. And to achieve this exact horizontal placement, the upper stage uses the Raman 2 liquid engine. It's this 3D printed marvel that acts kind of like an orchestra conductor, orchestrating tiny, hyper-precise adjustments. But precision in space comes with extreme thermal challenges. The combustion inside this engine reaches a blistering 2,700 degrees Celsius. That is hot enough to instantly vaporize normal metal. So to survive that, Raman 2 requires a deliberate and simultaneous cooling process. It runs 3 distinct protective systems in tandem: regenerative, radiative, and film cooling. Basically, it involves injecting fine jets of fuel along the walls to create a protective barrier of colder gas. It is a brilliant piece of engineering.
Section 4. The payloads to orbit, carrying science, tech, and heritage.
So, destination set, physics conquered. Now let's look at the fascinating payloads actually hitching a ride on this historic flight.
The rocket carried an incredibly diverse manifest. It brought up Scope, Skyroot's own tech demo, and Solaris, an Earth observation CubeSat. Internationally, it carried German deployment tech from D-Cubed. It even carried a highly experimental payload from Cosmos of Space, a soft robotic arm designed to test methods for capturing and cleaning up dead satellites and space debris, a real game-changer. And in a beautiful tribute to human heritage, Vikram-1 carried an 18-karat gold miniature rocket containing sculptures of Indian space pioneers, Sir C.V. Raman, Dr. Vikram Sarabhai, and Dr. APJ Abdul Kalam. And get this, each one was meticulously crafted to be smaller than a grain of rice.
Section 5. The historic launch sequence, Mission Aagaman, liftoff. After years of grueling qualification tests and waiting out the weather, Mission Aagaman, which fittingly translates to arrival in Sanskrit, finally commenced. The timeline of this launch sequence is so intense. At T-0, liftoff. Just 25 seconds later, hurtling at an altitude of 9 kilometers, the rocket slams into max Q. This is the period of maximum dynamic pressure, a brutal aerodynamic stress test for that ultralight carbon composite body. At 103 seconds, soaring 53 kilometers high, Stage 1 finishes its job and rapidly separates. And then, at just about 15 minutes into the flight, the liquid OEM cuts off, perfectly deploying those payloads into a 450-kilometer circular orbit.
And honestly, this perfectly executed sequence highlights the transition from brute force to total elegance. Step 1, roaring through the dense atmosphere using those solid motors. Step 2, at 120 kilometers up where the air is effectively gone, cleanly jettisoning the payload fairing because the satellites no longer need protection from atmospheric heat. Step 3, entering a quiet, combined coasting phase. And finally, Step 4, executing that precise orbital insertion using the liquid thrusters. It's an entire symphony of engineering, completely automated, wrapping up the whole shebang in just a quarter of an hour.
Section 6. A new era for space, the economic ripple effect. Look, this wasn't just a technical victory for one startup. It's a massive economic signal. The global space market is accelerating at an unbelievable pace, heading toward a staggering $1.8 trillion valuation by 2035. This explosive growth is largely driven by the insatiable demand for small satellite constellations. These are the hidden engines that power our modern daily lives, from the digital payments we make, to the weather forecasts we rely on, to the maps that guide us home.
And India has incredibly aggressive ambitions within that global market. Currently sitting at an $8 billion valuation, India's space economy is targeting over $40 billion by 2033. To get there, you absolutely need rapid, reliable, and affordable ways to get to space. As noted in the source material, rockets like Vikram-1 are essentially acting as the literal Uber to space. They offer on-demand launch capabilities that will allow the private sector to step up and capture this massive, growing global demand.
So, we've seen a rocket built from carbon composites, powered by 3D printed engines, successfully navigate through the violent stresses of the atmosphere to perfectly place satellites into a state of perpetual freefall. It proves, beyond a shadow of a doubt, that space is no longer just the domain of massive government agencies. Which leaves us with a thrilling question to ponder. As access to the stars becomes as routine and affordable as booking a commercial flight here on Earth, what incredible new global industries will be built next in the perpetual freefall of orbit? Thank you so much for joining me on this explainer, and I'll catch you on the next one.